So let's start. Today is lecture 2 on minimal surfaces. And as I said last time, today I will talk about how we can use complex analysis to study minimal surfaces and establish various very nice properties of these surfaces. So we're going to see something called the Weierstrass-Ennepe representation. So any minimal surface can be represented in a very nice way, like this. And we're going to say something about a Gauss map. And all of this is going to be able to help us produce new examples, interesting examples of minimal surfaces. So let me first recall from last time. So at the end we proved a proposition about how the coordinate functions are harmonic if and only if the surface is minimal, provided that you have an isothermal parameterization. So if x from U to R3 is an isothermal, so remember this means that E equals G and F equals 0, regular parameterized surface then x of uv is minimal if and only if each of the coordinate functions are harmonic. Okay? And you remember what this means, so if and only if. So I can write this condition in the following way. So xuu plus xvv equals 0. Okay? So you remember this. So this meant, of course, that xk uu plus xk vv equals 0 for all k is 1, 2, 3, where these are the coordinate functions of this vector x. Okay, so we have this. So it was suggested last time that maybe we can then find such harmonic functions and we can somehow produce examples. So we're going to do something like this. But so far it's not so easy because this is only true if the parameterization is isothermal. Okay? So maybe we find some harmonic functions, but we'd still need a way to test if it's isothermal, and we need a way to test if it's going to be a regular surface or not, because all of this is not at all obvious. And there is a very nice way of doing this using complex analysis. Okay. So connections with complex analysis. So what you're going to do is that if we have such a regular parameterized surface, then U is an open set in R2, and we are going to identify this with C in the standard way. So if you have UV lying inside here, you're going to send it to Z equals U plus I times V. Okay, so this you're completely used to. But then we want to study some suitable complex function so that we can say if this function will be holomorphic or not. This will be our point. So then we consider the following function. So at this point it's not obvious that this is what we should consider, but I will explain why we consider this. So consider phi. So consider phi k equals xk minus I, so xk u minus xvk for k equals 1 to 3. Okay, and then you set phi is this vector phi 1, phi 2, phi 3. And we will be looking at this. So each set phi k now is going from U, which we view as something inside C, and it goes to the complex numbers. And so this phi here has an image, and this thing will lie in C3. Okay? So now we have complexified everything by taking the partial derivative with respect to U and taking minus I as the partial derivative with respect to V. Okay. So I'm telling you we do this. So why do we do this? So let me just recall first what it means to be holomorphic and so on. Yeah, do this board. Okay. So each such phi k is holomorphic. What does it mean? So we call these Cauchy-Riemann equations. Okay, so we call that this phi k of uv. If you write it as f of uv plus I times g of uv, so in terms of its real and imaginary part. So this function is holomorphic if and only if. So what do we have? So we look at so you have taken complex analysis last semester, so maybe you will remember this. So f, and you take the derivative with respect to u, it should be equal to the derivative of g with respect to v. And if you take the derivative of f with respect to v, it should be equal to minus gu. Okay?
But we must assume regularity condition on the partial derivatives for the converse direction. We know if it's holomorphic, this happens, but this doesn't necessarily imply it's holomorphic unless the second partial derivatives, I think, are continuous. So.
Sure. We always assume that we are in such conditions so that this holds. So we're going to work with this. Okay, and so we also, so this recalls you that these Cauchy-Riemann equations are a condition for being holomorphic, provided these are suitably regular, which they will always be during this talk. And then we call also that exercise. So, okay, so this phi k is holomorphic if and only if partial phi k partial z bar equal 0. Okay? So I have to recall to you what these means. The differential not with respect to u and v, but with respect to z and the complex conjugate z bar. So what are these? Okay, so here, let me write it here. So where partial z is equal to partial u minus I partial v. Okay, z is equal to u plus iv. Then we have this. And partial z bar is equal to partial u plus I partial v. Okay, so this is how it's defined. And so you can easily see, so to check this, let's do it quickly. So this thing here, what would it amount to? So it amounts to taking, can you see this? Maybe I'll take the yellow one. So it amounts to partial u of f plus ig minus I partial v f plus ig. What is this? Well, it's equal to partial f partial u minus partial g partial v plus I partial g partial u plus partial f partial v. And so you see that this thing, so this is partial z.
There is a minus error at the first line.
That's the first line. Here?
Yes.
Ah, yes, I'm going to take the z bar. Yes. Thank you. So this is partial z bar of this. And so you get this thing here. And of course, this thing equals 0 if and only if the real part is 0 and the imaginary part is 0. Okay? So this has to be 0. This is the first line of the Cauchy-Riemann equations. And this thing has to be 0. This is the second line of the Cauchy-Riemann equations. Okay. So having partial derivative with respect to z bar equal to 0 is equivalent to a function being holomorphic. Okay? So this we're also going to use later. And also this has the added thing that we can also recall. So note that this phi k, which I wrote was equal to xk minus I, so xku minus xkv. And we can see what is this actually in terms of these operators here. Well, we can see that this is actually equal to partial z of xk. So actually what we are doing when I was looking at this complex function phi k is I was just looking at the partial derivatives of the coordinate functions in the direction of the complex coordinate z. Okay? So now it does no longer seem so arbitrary or so strange why I was looking at this thing. Okay, but in order to understand why I'm doing all of this, you will definitely want to have this following proposition. So this is the first key. So let's see, what do we want to do? We want to have some condition, ideally, for what it means for, so we want to choose some parameterization. And given a parameterization, we want to be able to say, is this an isothermal parameterization? Will it give a regular surface or not? And will these be harmonic or something else that is equivalent to being minimal, to the surface being minimal, okay? So we want all these conditions. And it turns out that when we phrase it in this language with complex analysis, using the complex coordinates, then we can get a very convenient criterion, actually. And the first part of this criterion is the following. Okay. So consider x a regular parameterized surface, or actually just a parameterized surface. Parameterized surface. Then the following holds. So the first thing is that the new coordinate functions here, phi k of z, so these are holomorphic. So here, of course, phi k as a function from u to c. Okay, these are holomorphic. If and only if the xk, which are functions from u to r, so here we think of u as lying in R2, and here we think of u as lying in C, lying in C and lying in R2, and these are harmonic. Okay, so this is equivalent. This new function that I've introduced, this new complex valued function, it's holomorphic if and only if the xk are harmonic. Second thing, so if I denote by, so x is isothermal, so the coefficients of the first fundamental form, E equals G and F equals 0, if and only if phi squared is equal to 0. What do I mean by phi squared? Phi, so this is not phi 2, okay? So this is the vector, so this means that phi 1 squared plus phi 2 squared plus phi 3 squared equals 0. Okay, so this is the scalar product of phi over 2. So this condition here holds for the coordinate function. So if I only compute this, and this is equal to 0, then this is equivalent to this being isothermal. And only if this holds, our criterion from last time holds, right? That harmonicity is equivalent to being minimal. Okay, and the last part is that if x is isothermal, and this is important, so if x is isothermal, then moreover, x is regular if and only if the sum from k equals 1 to 3 of phi k of z absolute value squared is non-zero for all z in U. So we have this amazing criterion, and then we will even have something stronger, some kind of converse that we will see later. But so let me prove this. So each of these take about 4 lines to prove. It's not very difficult. It's important to do it. So let's see. So proof. Okay, so we have phi, which is defined as xu minus I xv. Okay, now when I don't write anything here, it's the vector in C3. Okay, so this meant that phi k is equal to xuk minus I xvk, k equals 1, 2, 3. Now let's prove the first part. So xk harmonic, so it will be the same for every k. So what does this mean? This means that, by definition, xuu k plus xvv k is equal to 0. But then what does this mean? So this implies, well, I mean, this is equivalent to saying that, so now I take xku, and I take the derivative with respect to u. Okay, so now I have this. Okay, and this is equal to minus xkv derivative with respect to v. This is this equation. Okay, and then the other one would be x uk with respect to v is equal to x vk with respect to u. And this thing here, so it does not come from this one, but this one here, it just says that if you differentiate with respect to u and then with respect to v, it's the same as differentiating with respect to v and then to u. So this is automatic, okay? This is a well-known calculus fact. So, and these are exactly the Cauchy-Riemann equations, so this is equivalent to phi k, which was exactly this. So phi k holomorphic. So these are the Cauchy-Riemann. Okay? Okay, so now unfortunately I'm erasing this due to a small blackboard. Okay, so the second part is that x isothermal, if and only if this phi squared is equal to 0. So how do we do that? Well, we look at this phi squared, this vector. Then what is it? So phi k, so the components are exactly this. So then what you get is the sum, k equals 1, 2, 3, x uk squared minus, so let me write it like this. Sum k equals 1, 2, 3, x v k squared. So you're checking this while I'm writing it. Minus 2i.
I think it should be plus, because we have already
Should it be plus? Should it be plus?
Because we have minus here and I will be another line.
I don't think it's supposed to be plus. Let me finish writing it and you tell me if in 10 seconds you still think it's wrong, okay? So minus 2i, sum k equals 1 to 3, sum of x uk x vk. Okay, so we get this. Now it's correct, okay? But what is this? Well, this is just E, actually. So E, this is xku, right? And so on. Well, sorry, this is xu. This is what it is. And so this is equal to E minus G minus 2IF. In terms of, you remember the coefficients of the first fundamental form. So this is just equal to E minus G minus 2IF. Okay. So that means that, so if I note this star, so star is equal to 0, if and only if, what? Again, we have a real and imaginary part, and they both have to vanish. So if and only if E is equal to G, this is the real part, and F is equal to 0. And this is exactly what it means for X to be isothermal. Okay. So this finishes the part B. And then we have a part C. So for part C, so assume X isothermal. Okay, so we need to assume this, otherwise our proof will not work. So if you assume this, so now we make the following computation. So this sum of k equals 1 to 3 of phi k of z squared. So this is the thing that I claim that our surface will be regular if and only this, if this is non-zero. Now what is this? So let us write this in a different way. So this is actually just equal to sum of k equals 1 to 3 of xuk squared plus the sum of k equals 1 to 3 of xvk squared. And this is equal to e plus g. Okay? So already without using this isoformality, this means that so x regular. So by definition, x regular, it means that xu, the cross product of xu and xv, at some point, I mean, it's non-zero at every point q. Okay? But so clearly, this implies that, so again, now let's call this something, like double star. So this clearly implies that double star is non-zero. Because if it was 0, then both vectors would be 0 and the cross product would be 0. Okay? And then we have the other direction, and this is where we have to use the isoformality assumption. So conversely, so remember that we have E equals G and F, which is equal to XU, XV, equal to 0. Okay? So what does this mean? So let me write it out. So XU and XV. So what are we doing, by the way? So we are assuming that this double star here is non-zero. Hang on, let me write it. Okay, so we have this. So assuming, so this double star is non-zero, then it implies that these things, so XU, so either this thing is not 0, okay? So this thing is not 0, or XV is not 0. I mean, one of the vectors, at least, I mean, they cannot be identically 0, but this is equal to XV. Okay, so both of them are not 0. This is by isoformality, E equals G, okay? It's equals G. Okay, and on top of this, they are also not orthogonal. So let me write this in there. So XU and XV are not 0. So they are not 0 vectors. And by the F equals 0 assumption, by all these things, rather, are not parallel. So this means that XU, XV must be non-zero, because these are the only times. Only when this happens, this thing is 0. Okay. So this means that X is regular, because this is true for every point. Okay. Well, this argument doesn't see the point, so it's true for any point. Okay. So this means that it's regular. And it finishes. Okay, so is that clear so far? Okay. So now what do we want to do? So we have this result where we know that if we can find some holomorphic functions, phi 1, phi 2, phi 3, such that this phi squared for this vector, such that this condition equals 0, and the other condition, the C condition here, the sum of the module of phi k, this is non-zero, then we know that we have an isothermal parameterization of a regular surface. And by the part A of the proposition that I just proved, we know that this one is minimal if and only if these functions are holomorphic. So I just said if we have holomorphic functions satisfying the last two criterions, then it is also minimal. So it's an isothermal, regular parameterization of a minimal surface. So our strategy, the natural strategy now would be to try and see, can we find such functions in a suitable way? Okay, and the question, of course, is what do we get if we have such functions? Okay, so then we have the proposition 2. So suppose, well, I should write actually title, so this is going to be something probably, I mean, we're working towards something that's going to be called the Weierstrass Ennepe representation of minimal surfaces. So this would be a way in which we can actually represent any minimal surface in a very, very nice and convenient way that gives you lots of information. So first we have some preliminary result before we can come to the main theorem, which is the one called the Weierstrass Ennepe representation theorem. So suppose Z equals U plus IV, where UV is in some U, open set R2, we identify with C as before. So phi is equal to phi 1, phi 2, phi 3. For phi k, we continue to see holomorphic functions. Such that A, phi squared equals 0, and B, sum equals 1 to 3. So the same conditions as we saw earlier. This one is non-zero. Okay, for all Z and U. Then the conclusion is the following. Because, I mean, remember, what did we say earlier? So just so we know what we have proven and what we have not proven. So in the first proposition, proposition 1, we said, I give you a parameterization. Okay? So you have a parameterization already. You know it parameterizes some surface. And then I say, okay, we should define this phi in a strange way. We should say that phi is equal to xu minus I xv. And then we can read off information about this. We can see if it's actually an isothermal representation by looking at this condition. We can see if it's regular by looking at this condition. Okay, but I never said that if you just take any holomorphic functions satisfying this, then it should give me a representation. I mean, this is not the same thing, right? So this is not obvious. But it turns out to be true. So then there exists some x, u to R3, isothermal parameterization of a regular surface R3, such that, moreover, we can write phi in exactly the way that we had in the earlier proposition, such that phi is equal to xu minus I xv. Okay, so, I mean, this, if you just look at it quickly, it might look like I wrote the same thing as the earlier proposition, but it really is not, okay? So, just because I said if somehow you were already given a parameterization, then it satisfies such conditions. It's not the same thing, it's not at all, this is not as well as obvious, let's say. But if you have some functions satisfying these properties, then you can somehow come up with a minimal surface that is parameterized by them in a certain way. Okay, so this is, then there is a certain trick. That is not maybe so easy to see. So how should we construct this parameterization? So we are given such holomorphic functions and we want to construct a parameterized surface using it. in a canonical way. So proof. So really the first line of a proof will maybe be the one line that you should really remember from this lecture. Because if you understand this one line well, then you can sort of reconstruct everything that we're doing. But this line is good to remember from. So this line, I'm going to tell you now what will be the xk of uv. Because I have all these functions phi, and I want to construct parameterizers. So I should tell you what are the coordinate functions that I want to look at. So what I do is I look at the real part of the following integral. So I will explain what this means. So the real part of the integral from 0 to z of phi k of w dw. Note that I have some other coordinate here, okay? So let me write it. So phi k of uv, and here z is equal to u plus iv, okay? So u and v, the variable really is here. It's the endpoint of the curve along which we integrate, and then w here is something else, just the integration. So we look at this function. So what does this mean? So, well, let me just write. So where the integral means the following. The integral is taken along any path, gamma in u, which, and I forgot to write this here, so okay, so warning, so always assume from now on that u is simply connected. Okay, this is a sort of innocent assumption. It doesn't really cost you too much. But assume that u is simply connected. Because we want to take such integrals, and so what we want to do is we look at u here. This is u inside of R2, which we identify with z. And then we choose some arbitrary point, which I just take to be 0. I could have written z not here, something else. But I take it to be 0. For simplicity, I can always put u so that 0 is inside. And then I have my z over here, and I integrate along some curve gamma. Okay? And now the point is, so I choose some curve, and I integrate along it. This is what this integral should mean. But in order for this to be well defined, it should be invariant under which path I choose. Okay. So if I take gamma 1 here, this curve, and let's say I take the path integral along this one, then I want to know that if I take some other path gamma 2, I get the same result.
It's holomorphic.
It's holomorphic.
So the integral over a closed path is 0.
Exactly. So if I take gamma is equal to gamma 1 minus gamma 2, then integral over gamma of f of z is z equals 0 if f is holomorphic in u. But so why do I say that I take u to be simply connected? Well, if it wasn't, if there was a hole here somewhere, then this is no longer true. Okay. So if I had this kind of situation, maybe I would want to restrict my domain so that it actually was simply connected. Because if I go on different sides of some hole here in u, then this would no longer work. So I always assume that u is simply connected. And then we can define this integral in this way. So it's the integral, this notation means the integral along gamma of this holomorphic function, where gamma is any path from 0 to z. And since u lying inside of u, and because u is simply connected, the result is always the same. Okay? So this is clear. So any path gamma in u such that gamma of 0 equals 0 and gamma of 1 equals 0. I should write, okay? Not any gamma. But so this is what it is. Okay. And I do this also for k equals 1, 2, 3. So you look at this. And so now what do I have to do? Now I have to check So now I want to use the proposition that we had, right? And for that, the first thing I need to do is to check that these things are actually holomorphic. Okay, so step one. Okay, so this is not hard, but so phi k of W is holomorphic. Okay, so this implies, so this was by assumption. Okay, so we said we took phi k all these holomorphic functions. So then when you integrate phi k of W dW from 0 to C, then this is also holomorphic. Okay, because there is a sort of fundamental theorem of calculus that tells you that, so these are holomorphic, so we have an antiderivative, and you just take the antiderivative in Z minus the antiderivative value in 0. Okay, the antiderivative of a holomorphic function is holomorphic. So this integral is holomorphic. Okay, and then we recall further, so recall now that if we have some holomorphic function, so f of uv, say, equals x of uv plus I times y of uv, and this is holomorphic, then we want to show, I just want to recall to you that the real part of a holomorphic function is harmonic. Okay, so let's just write it out because it's very simple. Then by the Cauchy-Riemann equations, okay, we have the following: xu is equal to yv, and xv is equal to minus yu. But what does this mean? So this implies that xuu, so if I look at xuu, then this is equal to yvu. And if I differentiate the second one, I get that xvv is equal to minus yuv. Okay? But then what do I do? I can add these two up. This implies that xuu plus xvv is equal to, so I said I wanted to check that the real part, which is x, is a harmonic function, so I look at this. And then this is equal to yvu minus yuv. And this is equal to 0 because the order here doesn't matter. Okay, so these are the same thing. And so this shows that the real part of f is harmonic. And we could do the same for the imaginary part, but I won't need it here. So, but the proof is just the same. Okay, so using this, we said that phi k holomorphic implies that this integral is holomorphic. And then this implies that this real part of this integral is harmonic. Okay, so this one is harmonic, and this was, of course, equal to xk. So this is equal to xk. Okay. So z is always equal to u plus ib. So xk of uv is harmonic, okay, for all k equals 1, 2, 3. So this is the first step. So we have checked that it's harmonic. Okay, so soon I will put it all together. I will just give you one more piece of information first, and then you'll see how everything fits. So the second piece of information that I need to prepare before I can conclude with proof is step 2. So step 2 says that we have phi k is equal to xuk minus I xvk. So this is somehow a key step. So remember, in the first proposition, I said that give me a parameterization and define phi like this. But now I'm saying give me some holomorphic functions phi, and then I said let xk be the real part of such an integral. Okay, so then it will be harmonic, we just check. But we have no idea if this holds yet. Okay, so we need to check this. So in order to, what I'm doing, of course, is I'm trying to prove a converse to the first proposition. To this, I'll get a converse proposition. So I need to show that this holds. So V, so to see this, so now we need to mess around a little bit with these complex partial derivatives again, because of course, I mean, this, you know about this is a very simple expression, so if I took d/dz of this, then it would just be phi k, because this is the antiderivative that you write like this in integral form. So I want to know what d/dz is of this, but what I have here is the derivative with respect to u and derivatives with respect to v. So I need to relate derivatives with respect to u and v to derivatives with respect to the complex variable z. And so then we need to recall the following. So we had, now I first recall what I wrote in the beginning. Partial z is equal to this. And partial z bar is equal to the same thing, but with a plus sign. So now if I want to express partial u in terms of, oh, and actually I wanted to put 1/2 everywhere. So it's equal to, for convenience, I want to put 1/2. Because this will save me from writing 2 500 times for the rest of the lecture. Then we put 1/2. And then we have that, now if you look at, if you want partial u, then what is this? Well, you just add this one and this one, then these parts will cancel out, and you get partial u. So it's equal to partial z plus partial z bar. Okay, but if you apply this to a holomorphic function, so let's say that you have f here, so f is holomorphic, so assume that f is holomorphic, and partial f, partial u, is equal to partial f, partial z, plus partial f, partial z bar. But as I told you earlier, and I proved it, then this is equal to 0 because this is holomorphic. So this is equal to 0, so this is basically equal to partial f, partial z, or maybe I should write df, dz, sort of psychologically. And then we have the same thing if I take the derivative with respect to v. Then what do? Then I want this part to appear. So I want to take, I times partial z minus partial z bar. This is it, right? If I do this, of course I should put the f here. This is good? Okay, and so when I have this in the same way, this is equal to 0 because f is holomorphic. So if f is holomorphic, then this is equal to I partial f partial z.
I think it should be minus I.
No,
Minus n.
1 over minus I.
Yes. Good. I squared equals -1. So what do we get? So using this, I want to prove what I boxed here. So I want to compute the partial derivatives of this. So x, for each k, this partial derivative with respect to u is equal to partial u of a real part of this integral. But this is equal to the real part, so the real part in the derivative commute, okay? So the real part of partial z of this integral from 0 to z phi k of w dw, and this is just equal to real part of phi k of z. Because of what I told you earlier, this thing just becomes phi k of z. Okay, and then I have xvk, which is equal to partial v of the real part of this thing. This is equal to the real part of I partial z integral of 0 to c phi k w dw. Okay, so what is this? It's equal to the real part of I times phi k of z. But what is the real part of I times some function? It's equal to minus the imaginary part of that same function. Okay, so this is equal to, so xu is equal to the real part, and xv is equal to minus the imaginary part, but this precisely means this, okay? So this means that phi k is equal to xu k minus xvk for all k from 1 to 3. Okay, is this clear? Phi k is equal to its real part plus I times its imaginary part, so it's equal to xu minus I xu by this calculation. Okay, so now we have this. And now how do we finish everything up? So we have step 1 and step 2. So we know that this is true, and we know that these things here are harmonic. Okay, so to summarize, so we have psi equals xuk minus I xuk. We have xk of uv harmonic. Okay, and we have, by hypothesis, we have phi squared equals 0, and we have sum of k equals 1 to 3 of phi k of z is not equal to 0 for all z. So we have, these were all hypotheses, right? And then I define my surface in this way. So now we have a parameterized surface where these are harmonic, this holds, and so on. And so by proposition 1, this is proposition 2, right? So by proposition 1, x u to R3 is an isothermal regular minimal surface. And this ends the proof. Okay, so now we have seen that you can use this trick of taking the coordinate functions of a parameterization to be the real part of the holomorphic functions, provided they satisfy these conditions. So now we come to the real part of this representation, the Weierstrass-Ennepe representation, which will be about choosing two functions. One function will be holomorphic, and one function will be meromorphic. How much did you hear this? I don't remember the word meromorphic. One will be holomorphic and one will be meromorphic. So I will recall this now. Yeah, I will recall what it means. So recall that some function, which I will call g, because this is the notation standardly used in this representation theorem, function g from, so this lies inside C, okay? So some function which is the domain of C into C is meromorphic if it is holomorphic. So holomorphic, I already recall what it meant, right? So it's holomorphic on X minus sigma, where sigma is a discrete set of isolated points. Okay? So sorry, why did I write X? On U minus sigma, where sigma is a discrete set of isolated points. And these points are called, as you know, the poles of the function. So this is where we take the value infinity. Okay? So this is what it means. So locally we can write the following. So locally, recall that if f is holomorphic, so f u c is So I will just recall to you that it's analytic and be Laurent expansion and things like this. So if it's holomorphic, then it implies that f of z is equal to locally around some point p in U. Then we can write it as the sum from k equals 0 to plus infinity of ak times z minus p to the k. Okay? So you can do this. And if f, now g, sorry, is mirromorphic, then g of z, is there a question? Sorry?
From infinity to, no, if meromorphic, so.
If meromorphic, yes. But so if meromorphic, so it's from minus infinity to infinity, but if it goes all the way to minus infinity, it means it has an essential singularity, okay? But we want to consider poles. And poles means that it stops at some point. It stops at minus 23, okay? So this is the lowest one. And then this will be the order of the pole will be 23. So let me write it like this. So it's a minus m, z minus p to minus m, plus a minus 1 to z minus p minus 1, and then plus the same thing as over here, so k equals 0 to plus infinity, ak z minus p to a k. So you have this negative part, and this is called the Laurent expansion of the series. Okay? So Laurent expansion. And this m here, so the last one, so to speak, the m, which is such that a minus m is non-zero, is called the order of the pole. Okay, this is some finite number. And the order of the zero of a holomorphic function, this you know what it is. Okay, so we're going to need these notions when we express the representation theorem. Okay. So the main theorem, top, which is the Weierstrass NFA representation theorem, is the following. So let f be a holomorphic function, and g be a meromorphic function, so in particular it could be holomorphic as well, okay? So if you think it's easier to think of it, you can say both are holomorphic. But this one is allowed to be meromorphic, this one is not allowed to be meromorphic, okay? And okay, such that, and we have two conditions. So the first condition is that if P in U is a pole of G of order n, so it means that G looks something like this. Locally around P, you have such an expansion. Then P, that same point, is a zero of f of order at least 2m. Okay? So it has to be at least twice the order. So P is a zero of f of order at least 2 times f. Okay, so this is the first condition. And this will imply that this, just for the proof later, this will imply that fg and fg squared are holomorphic. Okay, so this is kind of why this condition is here. We will need this. So 2, the second condition, is that if P in U is a 0, so this second condition is that these are the only zeros of f. So if G doesn't have a pole, then f does not have a 0. Okay? So if P in U is a 0 of f, then P is also a pole of G. Okay, so we don't want any other zeros. So this is the thing. Okay. So let's see. What is then the statement? So we have these two conditions. And then the statement is that we can get regular parameterization, regular isothermal parameterization for a minimal surface using f and g in the following way. Then x1 of uv is equal to the real part of, let's see, so real part 1/2 0 to z f of w is 1 minus g of w squared dw. X2 of uv is equal to real part of 1/2. So they will all be integrals like this, okay? So f of w, so let's see, this is I. So this is not 1, this is I here. So I over 2, f of w, 1 minus g of w squared, dw. And then x3 of uv is equal to real part of the integral from 0 to z of f of w, g of w, dw. Okay, sorry, this is horrible. I should write it somewhere else. Write it here. So then this will define coordinate functions for a regular isothermal minimal surface. Okay? So and x3, I'm writing it again because I think it was terrible to write it there. So is equal to the real part, the integral of f of w, g of w, dw. So they yield x of uv is equal to x1 uv, x2 of uv, x uv, regular isothermal minimal surface in R. Okay.
Just the same thing, but there is no half here in x3?
There is no half.
Okay.
I mean, it's not the same thing. I mean, so this is f times 1 minus g squared. This is I over 2, that's f times 1. Oh, shit. There's a plus here. Okay. So this is I1 plus, and this is f times g. Okay. So you have 3 different coordinates, but you can all express them in terms of f and g. And this is kind of a miracle. And I mean, you see that before we prove it, just look at the power of this thing. It means that, you remember I told you for 100 years, there were only, apart from plane, there were only 2 examples known. There was the catenoid and the helicoid. And it was really difficult to find more examples. So now if you come up with this brilliant theorem, then it is really easy to come up with more examples. Because once you prove this theorem, I ask you, okay, now give me some non-trivial new example of a minimal surface.
Choose your favorite holomorphic functions, and I can create such a G which satisfies all of these.
Exactly. So what you choose, so for example, f of z, so some application, you can take f of z equal to, so it should not be always 0, because we said, so the meromorphic function needs to be meromorphic, so the poles can only be in isolated points. And we did not want f to have any zeros that were not poles of g. So f of z, we should not take it to be 0, but we can take it to be everywhere 1. Okay? This is a function equal to 1. And then we take g of z, does not even, we don't even have to complicate things. We don't even have to take it meromorphic and consider the poles and check all these conditions. We can just take it to be equal to z. Okay, because if we take it to be equal to 1, then all of this will just be trivial. So this does not work. Okay? So we take it to be equal to z. Okay? And then what we get is something called Enneper's surface, because, okay, we proved this theorem and then he applied it very nicely. And then you get something that looks, I mean, very interesting and very complicated. So you have this very simple f and very simple g, but you get something which is a highly non-trivial, very fascinating example of a minimal surface. Okay, so we'll see this. Let me write it. So this gives Enneper's surface. I encourage you to find a picture of this online, because I cannot do it. Okay, so the proof. Let me now give you some idea of the proof. Actually, I didn't finish stating the theorem even. So it's even stronger, so okay. So now I only stated the first part. So I stated that if you have such f and g, then you get minimal surface. But then also, conversely, it takes me the whole blackboard to state the theorem. Conversely, so every regular isothermal parameterized surface S in R3 can be written in this form. Okay, I forgot the last part of the theorem, which is also very striking. So if you have such f and g, you get a minimal surface, and for any minimal surface, you can write it in this way. And the great thing is actually that you can recognize a lot of things. So if you have a surface that you absolutely do not understand, and somebody says, hey, I'll help you. I'll give you f and g for this surface, because there is an f and g corresponding to every isothermal minimal surface, then you can know a lot of things about this surface. For example, if you know g, only by knowing g, you can compute the Gauss map with a very simple formula. This is very nice. Okay. So let me erase this. Remember this thing I just erased, that f and g are homomorphic and f g squared are homomorphic. Okay. So, proof. Okay. So, I know this theorem is kind of a mess to state, but so just, it looks somewhat nicer if you write it like this. So f1, this phi 1, so I mean, the parameterization will be the real part of the integral of phi k. So phi 1 is 1/2 f, 1 minus g squared. Phi 2 is equal to I halves f 1 plus g squared, and phi 3 is equal to f times g. So this is what we have. So first note that phi k are all analytic by conditions 1 and 2. And this is precisely because, I mean, so the first one, it's f minus fg squared. So fg squared are analytic. And so f minus fg squared is analytic. V multiplying by I doesn't change anything. F plus fg squared is analytic, and f times g is analytic. So all of these functions are analytic. I don't know why I just changed, so I should write homomorphic rather to keep with the changed notation, not to confuse you. Okay, so they're all homomorphic. Now, the second thing is that, moreover, phi squared equals 0, and the sum of k equals 1 to 3. So again, I mean, we keep coming back to these conditions that I started the day by establishing, but these are always important things to compute, okay? Where phi is equal to phi 1, phi 2, phi 3, as usual.
why we need a second condition? For example, from first condition we can got this one.
Yeah.
Fg and Fg square is holomorphic. But
you're right. So actually, we need the second condition for the converse for this last part of the theorem. Yeah. So it's yeah. So I will stop. You just use one here, and then you'll use two later at some point. Okay. So thank you. So for example, so this you can see through direct computation. Okay. So let's just, try the first part. So this is computation. I don't think this is very good. Just for computation. So just pi squared, what is it? So it's just 1/2 f 1 minus g squared minus I over 2 f of 1 plus g squared plus fg squared. But what is it? So okay, you do a computation and I read the computation I just made because I made it. So this is equal to 1/4 f squared times 1 plus g to the 4 minus 2g squared minus 1/4 f squared 1 plus g4 plus 2g squared, and then minus 1/2 why do we have 1/2? Minus f squared g squared plus. Okay, good. Which is equal to f squared g squared minus 1/2 f squared g squared minus 1/2 f squared g squared is equal to 0. That's okay? I might have written something.
Plus, I think, plus 1/4 f squared, because e squared is minus 18 and I squared.
I squared is minus.
Second term,
okay, so anyway, somehow this should be 0 if I made some mistake. I squared is minus 1.
This minus is true. In the first formula, there should be plus. Just we need to find plus square plus.
Yeah.
This is minus is true.
Yes. In the first line.
First line.
Is correct. No. The second one. The second sentence.
Yes.
Second term.
Above, just above.
Above.
Just, yes, this minus should be plus.
This minus should be plus.
Because
Yes. Okay. Very good. Okay. So now this became correct. Okay. Thank you. So good. So now we have this computation and this is equal to 0. Okay? And in the same way, you can also show that this is equal to 0. Okay. So as you see, I've done absolutely nothing. This is just taking the hard part, which is, I told you what should be phi 1, phi 2, phi 3, and you check this. Okay. And so the same thing, the other part. And then let me just say something about the converse. Okay, so let's just note. So why are we done? So we check that these are analytic and this holds, and then we are done by the previous propositions. Okay, so this is done. So proves first part. Okay, by previous proposition. So now conversely, I just should take you check this trick. So if phi k are holomorphic such that phi squared equals 0 and the sum business, this condition is non-zero. Okay, for all z in U, then we set, so now we have to use these phi 1, phi 2, phi 3 to construct f and g. Okay? And so if you think for a while, you will, or I don't know, a very long while possibly, then we should set f of z should be equal to phi 1 z minus I phi 2. Okay, so let me drop the z. So we should just say this is equal to phi 1 minus I phi 2. I don't want to confuse you with being squares or something, but these are the indices. Okay? And g should be equal to, So there are two cases actually for G. So G should be equal to phi 3 divided by phi 1 plus I phi 2. And this is the exceptional case. So this is if phi 1 of Z minus I phi 2 of Z is identically 0. Okay. Now I switched the indices to writing it down because sorry about that. So and otherwise phi 3 over phi 1 minus I phi 2. Yes. So what am I writing here? I'm saying that essentially you want to put G equal to this, but you cannot allow that this is the zero function, because then it is not meromorphic. I mean, so zero function means it's zero at every point. So then it's not meromorphic because it's everywhere infinity, this function. Okay? I mean, so if this is everywhere zero, then you do this instead. And then this is not everywhere zero because, you know, if this is everywhere zero, then this is not everywhere zero. Okay. So then F and G satisfy the conditions 1 and 2, meaning that, okay, so if we have a pole of G, then we also have the 0 of F, I degree, and so on. And phi is equal to F halves. Let me write this on the next word. So now I am saying this, I mean, a little bit quickly, so I'm going to not do all the computations here. I'm just going to tell you what you would have to do, and why. And then this is possible to check. I mean, it's quite easy. It's just like this. Because then I want to say something about the Gauss map. So, and this phi is equal to F half times 1 minus G squared I 1 plus G squared and 2G. So this is the representation, exactly the one that you wanted. Sorry?
No.
Yeah. Okay. So this is exactly what you wanted, and this I will leave to you as an exercise. Okay. So this is an easy exercise. Just check this. Okay. So this proves the theorem modulo some basic calculations. Okay. So now let's just check some examples and applications of this. So for the last 15-20 minutes, let us discuss this. So first of all, so I've already somehow told you about this NFA surface and how you can get new examples. So maybe I'll start with that one since it's no longer a surprise. So, so example, NFA surface. Okay. So take F of Z equal to 1, and G of Z is equal to Z. Then you get X of Z is equal to the real. So I mean, this is always very long to write, and it looks kind of horrible, but I mean, it's really not that bad. So real part 1/2 equal from 0 to Z of 1 minus W squared dW. And then the second coordinate is real part of integral 0 to Z of I times 1 plus W squared dW. And the last coordinate is real part integral from 0 to Z of F of W, F of W, G of W, which is just equal to W dW. Okay, so you get this representation. And then what do you do? I mean, okay, now you have these integrals and it looks kind of horrible, but of course you can compute these integrals to make it look like something you recognize. So you compute these integrals, and then you show, and I'll write what you get. So you compute it, and you get, so exercise, I'm calling it exercise just to check all these computations and not to justify it. So that's this x, this gives the surface x of uv, which is equal to 1/2 times u minus u squared over 3 plus u v squared minus v plus v cubed over 3 minus u squared v, and the last coordinate is u squared minus v squared. So you get such a parameterized surface. And when you see an expression like this, it looks very basic, and you think like, okay, maybe I can write down anything that looks a bit like a polynomial, maybe I can find one of them that is minimal and so on. I mean, this just goes to show that this is very basic, and you can check. So exercise again, so exercise, you can check directly that h is equal to, I haven't even written h once today, but you remember, check that the mean curvature is identically 0 for this. But, I mean, as history shows, you do not really find this unless you're, I mean, it's like winning the lottery to find this. Unless you understand why, and this beautiful connection with complex analysis, and this beautiful Weierstrass-Ennepe representation theorem is a nice way that actually characterizes these surfaces. They can all be represented by such f and g, and then this one comes just like that, by taking the simplest example. Okay, so it's this one. Then we can also, example 2, we can reproduce also the examples that we checked last time. So we can reproduce, for example, the catenoid and the helicoid. Okay, so if you take f of z is equal to e to the minus z, so this is a holomorphic function in the whole plane, okay? And then g of z is equal to e to the power z. So again, I mean, here they were both holomorphic. Again, they are both holomorphic. Everywhere, okay? So this meromorphic business, by far, it's not a requirement in order to get something interesting. Often, without poles, you can get many very nice examples. So all the conditions are automatically satisfied on what happens by the poles and so on. I mean, it's very easy to check. Then you get that x of uv is equal to a real part of, so let me write it like this. So you have the integrals 0 of z of e to the minus w over 2 times 1 times e to the power 2w dv. And then let's continue here. And then after this one, the second one will be I e to the, so integral, sorry, from 0 to z. This is e to the minus w times 1 plus e to 2w. Okay, so that's great. To the dw, and the last one will be f times g, but f times g is just 1. So it's just equal to dw. Integral of 1 dw. And now I wrote it like this, taking the real part of this vector, I just mean the real part of everything that's inside. Okay? And this, you can check that this is actually equal to, so it's equal to the real part minus e to the z plus e to the minus z over 2. And then I think without the minus, so I over 2 e to the z minus e to the minus z. And then z. So it's equal to the real part of this. Okay, and this is equal to, no, sorry, maybe not the real part. I'm not sure. Okay, not the real part. So it's equal to the real part of minus cosine hyperbolic. So again, I mean, all of this you need to check, which is equal to minus cosine hyperbolic u cosine b minus cosine hyperbolic u sine b, and finally u. Okay? And now when you have something like this, cosine b, something like this, sine b, then you start thinking that this is you start seeing that this is a surface of revolution, and this is actually equal to the catenoid if a equals 1. Okay? And then compared to the example we did last time, we have switched the role of u and v. So unfortunately it became like this with the notation that they used. So u here is in minus infinity, infinity, and v is in 0 to 2 pi. And you get this catenoid as a minimal surface. So likewise, exercise. So you can get the helicoid. So f of z equals I e to minus z, and g of z is equal to e to power z. The same thing gives the helicoid. So you see that they're actually very similar. So here it's just, the only difference is that I put an I here. And then I get the helicoid instead of the catenoid. Actually, you can have a family, you can actually deform the helicoid into the catenoid by just putting something here like e to the I theta something, okay? And so you get the family deforming the helicoid into a catenoid. I can show you pictures of it afterwards. I'm not going to show on the camera. So it's actually very beautiful. And they are called conjugate minimal surfaces. They are very similar representation. Okay, so any questions about the examples? Otherwise, I will just say one last thing here about the Gauss map. So once you have this WE representation, base/inner representation, you can very easily read off the Gauss map. Okay? So this is the last thing that I want to say quite quickly. And then once I have said that, I think that you have gotten at least introduced. I mean, if you're interested, you definitely know what you can look at to look more at minimal surfaces. You will have already seen quite a lot for an introductory course. So analyticity of the Gauss map. So of course, the Gauss map is the map that sends the point to the normal vector, point on the surface to the normal vector at that point. Okay? And this is, of course, the most fundamental map to understand for a surface. So, I mean, if you understand what the normal is and how the normal behaves at every point, then you essentially understand your surface. Right? So this is extremely fundamental thing. And the point now would be that if I give you f and g if I give you a minimal surface, then there is some f and g such that it can be represented in the Weierstrass-Enneper way. And if I give you f and g, or actually if I only give you g, then you can get the Gauss map from this. So first recall, so I need to just tell you about stereographic projection. So recall stereographic projection. So I know you've had this even on your homework in this course. So you should know it. So it's sigma from S2 minus a point, which is usually called the North Pole, okay, to C, which is defined. So there are some different conventions. Okay, so I like to draw it, but essentially you have this, here you have the North Pole, and you meet the point here, P, with the point P prime down in the plane. So here this one is the point X, Y, Z in the unit sphere, okay, minus the North Pole. And this is the point X, Y in R2, which I can then identify with the complex plane. Okay? And then we have, so the image, so this geographic projection, it sends P to P prime. Okay. So remember this. And there are formulas, as you have seen in your homework sheet, for how you map X, Y, Z to this one. So you have formulas. You have sigma of X, Y, Z, so the projection of this point on the surface of the sphere down to the plane, it is equal to 1 over 1 plus x squared plus y squared. Then you have, no, sorry, this was the other one. This was the inverse I started with. Okay, so it's equal to x over 1 minus z and y over 1 minus z. Okay, so this is the projection. And then what we'll be interested in is the inverse, the one that I started writing a bit too quick. Okay, and the formula for the inverse is following. And then sigma inverse of xy is equal to 1 over 1 plus x squared plus y squared times 2x, 2y, and x squared plus y squared minus 1. And note that this is equal, so if I put now z equals x plus I, y, then, for example, this is the norm squared, right? So this is equal 1 over 1 plus the norm squared, 2x, that's 2 times the real part, so this is z plus z bar. 2y, you can obtain it by minus y times z minus z bar. Okay? And this last part, well, it's just the norm squared minus 1. So you can write it in this way. Okay? And now the theorem, so the analyticity of the Gauss map, so this would be maybe the second main theorem that I just want to mention in this lecture. This is very, very important, very nice. So suppose S in R3 is a minimal surface with this, I'm abbreviating it like this now, Weierstrass-Ennepe representation. Given by FG. Okay, so instead of always writing out real part of these horrible integrals, we just write like this. Representation given by f and g. Okay, and here just the remark is that, so we view g here. So g is a function which is meromorphic. So in some sense, I mean, u is from g goes from u, which is inside C, and it takes values in C union infinity. So it can take the values infinity, and then we can look at the sigma inverse. So the inverse of this geographic projection times g. So what does it do? It goes from u. So first we take g. It goes from u, and then it takes goes to C union infinity. Yes, because I mean the standard thing here that I'm not telling you is that we can also assume that, you know, sigma sends North Pole. It sends it to a point called infinity. So this is the compactification, okay? This is how you get the Riemann sphere. So the north pole, you identify it with infinity, and all the other points are identified with something on the complex plane. Okay, and this is why you often see writings like S2 is equal to C union infinity. Okay, so this is the compactified sphere. I don't know how many times you've seen this, or if you're used to this yet, but this is how you would see it. So this thing, it goes from U to C union infinity, and then I can consider sigma inverse here. So this is G. And then going from sigma inverse, it takes me from C union infinity to the sphere, including the North Pole, okay? So if I was somewhere in the C part, then I would end up somewhere not in the North Pole, and if I was at infinity, I would end up in the North Pole, okay? So this is how it goes. So you see this as a map from U to S2, okay?
And this defines a map from our surface to S2, right?
Yes, so this defines a map from our surface to S2, exactly. Okay, and what other map goes from our surface to S2? Well, the Gauss map, right? So this is the same domain, because it associates a normal, which is an element in S2. Okay, unit normal. So the claim now is then the unit normal n, which is xu, xv. Okay, so you know this. So the unit normal here, it's actually equal to the following thing. It is equal to 1 over 1 plus modulo of g squared times g plus g bar minus I times g minus g bar and modulo g squared minus 1. Aha, okay. But this looks awfully similar to something that we have here, right? This looks like the inverse of the stereographic projection. And so this, now the way you should think about this is that this is actually equal to sigma inverse of G. So the normal is actually equal to this G up to understanding the proper identification of how you identify the complex plane, union infinity with the sphere using the stereographic projection. The stereographic projection is the bridge that allows you to see that, to identify this function G from the representation theorem with the normal. And so this function G, for example, in Enneper's surface, right? It was G was equal to Z, F was equal to 1, and G was equal to Z. So then this means that the normal is just this, okay? And G was a holomorphic mapping in this case. And so actually this normal, as we vary the point, the normal also varies holomorphically. So this is sort of how you should interpret this theorem. One of the big things is that if you have a minimal surface, then the Gauss map is holomorphic.
But that's not true because Z bar is not holomorphic.
Because Z bar is not holomorphic.
So if G is holomorphic, then this is not necessarily holomorphic because I have a conjugation.
Yeah, but this is why you have to understand it in the appropriate way. I mean, so I'm saying these things, but you always have this bridge, right? And so what you know, when you ask people working on minimal surfaces, they will tell you, oh yes, the Gauss map, it's holomorphic. But then there is this caveat that you have to understand what it actually means. So you always only work with holomorphic maps from C to C. But when you work with holomorphic maps from C into something which is actually a complex manifold, which is the sphere, then actually, so a meromorphic function on C is the same thing as what we call a holomorphic function into the sphere. So it is in this sense that I use the word holomorphic. So I use it a little bit sloppily in a sense that you are not used to. But still this formula is true. So if you want to understand something precise, you understand this formula, okay? And then you can keep in mind that there is an interpretation of this Gauss map as being a holomorphic function as a function from C into S2, not as a function from C into C, okay? Okay, so I thought it was important to mention this, at least at the end of the lectures. And yes, so we have seen the representation theorem. We have seen that if it's minimal, so we understand the minimal surfaces, we understand how to give new examples. There are more that I could give you, that you could check. I mean, you can choose an F and a G, and you can do it yourself, right? Now that you have the theorem. And you have also seen that if you know F and G, then you can write the unit normal in a very convenient way. Okay. So for example, this is the unit normal for the n upper surface. Okay, so it's time, so I'll stop.